All right, so today we're going to start talking about calculating the wave function in the universe when we have interactions. And let's actually begin again with just calculating the, just in a simple example, just calculating the wave function in flat space. Remember, we're still trying to do exactly the same path integral with the fixed boundary conditions at the future slice at eta equals 0. So let's say we have a theory just for fun, a massless scalar field, and we have a cubic coupling. Okay. So the first thing we're going to do is we're going to expand phi as that free phi classical that we had before, plus some interaction delta phi. Okay? And so what's the first thing that's going to happen? Then S is just going to equal, so I'm just expand this out, right? So from the quadratic part, what I'm going to get is S of phi classical free. And then I'm going to have some interactions. Well, then I'll have now a kinetic term for this fluctuation. So I have d delta phi squared. Now I can expand everything else out here. So for example, here, I'll just be a little schematic. I'll have a g phi classical free, maybe, phi classical free cubed plus phi classical free squared delta phi plus phi classical free delta phi squared plus delta phi cubed. Oh, thank you very much. Oh, great. Much appreciated. And so what we're left with doing is we now want to, so now we want to do the path integral over delta phi, just e to the I action, which now just depends on delta phi. But now what are the boundary conditions for delta phi? Well, we've already, with phi classical free, we've already ensured that we're matching the correct boundary condition that eta equals 0. So the boundary conditions for delta phi are that delta phi as eta goes to 0, or eta naught, well, 0 and eta naught I'll use interchangeably, goes to 0 now. But still, of course, delta phi still only can have those positive frequency modes as we go off to minus infinity. Okay? So delta phi, the usual, as we go to minus infinity plus I epsilon infinity, this has to go to 0. Okay, so that's what we want to do. Now notice that the first piece of this, the S classical free of phi, was already giving us. So this is psi of the boundary phi, and so this is already equal to. So the piece of this, which is just e to the I S classical, this is already giving us the e to the minus, this is already giving us an e to the minus phi squared times whatever we got here, whatever the Gaussian part of, I don't know what to call it, doesn't matter. Gaussian part, which can depend on k in some interesting way. So all the rest of it is giving me the, all the rest of it in the exponent, we're doing this path integral, everything else in the exponent is now going to depend on phi. This is the, again, we remind you that we said, for example, in this case, phi classical free of eta is equal to phi e to the I k eta. Right, this is the boundary value, so things are going to depend on that phi. So we'll have things that have 3 phi's, things that have 4 phi's, and so on, okay? And so these are the things that we're trying to calculate by doing that path integral. So for example, let's look at the first piece. The easiest piece is just this. It still doesn't involve doing any path integral over delta phi. It's just the integral over, it's just the integral of phi classical free cubed, right? Yes. Sorry? Oh, I'm sorry. This was, that's right. This was S, thank you. This was S free. This was just coming from the d phi squared piece, okay? So for instance, and so we'll do these calculations. We'll do all these calculations using Feynman diagrams, okay? Because we're just doing the path integral over delta phi. Okay, so we're just doing them using Feynman diagrams. But the easiest one doesn't involve any delta phi at all. So this is a surface at eta equals 0, and is just a piece with phi classical cubed, right? So here there's there's some integral over some time eta here, and then there's a phi classical, there's some phi classical free cubed. Okay, so there's one of these for each one of those factors. Okay, sure. Okay, so I'm drawing this so that there's a phi classical free cubed. So each one of those is a factor of phi classical free. So for instance, from here, what I would get is an integral d eta, and each one of those phi classical frees is e to the I k1 eta, e to the I k2 eta, e to the I k3 eta, and I've immediately gone to momentum space, so there will be some overall delta cubed k1 plus k2 plus k3 for the vectors that I'm not going to keep writing down again and again. And the integral is from minus infinity to 0. Okay, so that's the first contribution that we get. There's an IG in front of the whole thing, and so this integral just gives me g over k1 plus k2 plus k3. Right? So that's the first interacting contribution. But there are other diagrams. So now there are diagrams involving integrating over delta phi. So for instance, from this piece, phi classical free squared delta phi, this is like a vertex involving just delta phi, right? So I would draw a diagram like this. And to emphasize that this is delta phi, maybe I'll draw it as a dashed line here for now, okay? So here now there are two factors of phi classical free, here and there, and also here and here, there and there. But here I have to have a delta phi propagator. And so what is that propagator? Now that's exactly the thing that we calculated yesterday, right? That is a 2-point function for delta phi, but with the important boundary condition that delta phi vanishes at eta equals 0, and that delta phi has the correct behavior as we go off to minus infinity, okay? So this is the, so if you like, in ADS language, these are the bulk to boundary propagators are just the free propagation, and the bulk to bulk propagators are that object that we computed yesterday, okay? So this propagator is just the thing that we computed yesterday. So there'd be some eta and eta prime, and so we'd have integral eta d eta prime e to the I k1 plus k2 eta e to the I k3 plus k4 eta prime, and then it'd have a single factor g of eta and eta prime. Yes? No. Well, we computed two different things. Yesterday, by the end of the lecture, we are looking at just what the final vacuum wave function was, right? The vacuum wave function just depends on the boundary value of phi. And then talking about correlators, we're just talking about an expectation value on the boundary. Okay. Earlier in the lecture, when we just had the general discussion of the harmonic oscillator, the time-dependent harmonic oscillator, if you remember, I paused to say that, let me write down the formula. You might remember that we should work out what the general propagator between eta and eta prime looks like. And so, for instance, in this free case, g of eta and eta prime was theta of eta prime minus eta of eta minus eta prime e to the I k eta e to the minus k eta prime plus theta of the other way around e to the I k eta e to the I minus I k. Sorry, I did this wrong. K eta to the minus I k eta prime, and then minus e to the I k eta e to the I k eta prime. Okay, so this is a propagator. Again, it has the structure of having three terms: time past, future, and this homogeneous piece. These first two terms are familiar from just normal sort of time-ordered product, giving you propagators. We derived it from scratch yesterday by the little jump condition, solving the equation and just doing the jump condition. This piece was there to ensure that the boundary conditions at eta equals 0 were correctly satisfied. Okay? All right, so then we can keep, yes? Because we don't have that vertex. That's precisely because we're expanding around the free classical solution, so we don't have any tadpoles. Okay, okay, so we can have diagrams like this. And we don't have to keep drawing them dashed. So whenever it's on the inside, we know we're supposed to use the bulk propagator. Whenever it goes out to the outside, we have to use the bulk boundary propagator and so on. Okay, is that clear? So let me now write. So this was just in the flat space. But let me just I just did that so we could just write down the full expressions simply. But let me write down what the general rules are. This is just the general Feynman rules for the perturbation theory of calculating the wave function in a totally general time-dependent background. So the general rule is that psi of phi is e to the minus whatever the Gaussian piece was, phi squared, plus, and then we have phi 1, phi n, and some f1 through n. So these are the things that we're computing. And so if I have a diagram that, some complicated diagram that looks like this, it doesn't matter. Okay? We have integrals over all the etas for the vertices. Okay? We have that factor with whatever the vertex factors are. And all that matters is to remember that the bulk to boundary propagator is just what I was calling yesterday the free solution with the proper frequency at minus infinity, f plus of eta over f plus at eta naught. And the boundary to boundary propagator between some eta and an eta prime is just g of eta and eta prime, whose general expression for the totally general time-dependent problem we gave yesterday. Okay? Any questions about this? So let me just pause to say that if we weren't integrating, so first of all, if it wasn't a time-dependent problem, so this is also true in flat space. We just did flat space. Again, if we weren't putting the cutoff here on time, if we let the time go to infinity, then this is nothing other than a rewriting of standard Feynman diagram calculations for scattering amplitudes, where we've chosen to do the calculation by remaining in position space for time while only going to Fourier space for position. Okay? So here what we've done is go to Fourier space for position because there's translational invariance in position, but we've stayed in time space for time because there's no time translational invariance. But if we remove the boundary, we would just be computing standard scattering amplitudes. So A, we put the boundary here, so we've broken the symmetry between time and space. And B, if we have a general time-dependent background, we have these modified bulk-to-boundary propagators and boundary-to-boundary propagators derived from the free theory, as we discussed yesterday. All right. Yes? Yes. That's right. That's right. That's right. Well, but there is a boundary. I mean, that's if you're like in that space, I'm talking about the boundary at t goes to plus infinity. Okay. Okay. Now, in the next lecture, we're going to do a lot more with simple models, and we'll do many more perturbative calculations of this in simple toy models, kind of an extension of what we're just talking about here. But in this lecture, I actually want to focus on a simple example in de Sitter space. And this is what's close to being relevant even for inflation. If we imagine the inflaton is coupled to some massive particle, this is what we qualitatively talked about in the first lecture, but I want to now address it here. So I want to imagine I have a scalar field phi, which is light, and is coupled to some massive scalar field sigma. So this is going to be light, and in fact, to make my life simple, I'm not going to assume that it's massless. I'm going to assume that it has the mass squared equal 2, so that it's conformally coupled. Now, the calculations are not much more difficult if it's massless. They're very closely related to each other, but this will allow us to simplify the problem a little bit. Okay? Remember, when it was conformally coupled is when its propagator was as simple as possible and so on, just because it was conformally related to flat space. But this is going to be a general scalar of mass m. So mass capital M. Okay? And so what I'm interested in is the 4-point function that's going to be the star of the show for this lecture, the 4-point function now of this sort, with phi on the outside and sigma on the inside. All right, so what is this? Just by our rules, this 4-point function is equal to, so it depends on k1, k2. Actually, we can quickly see what it depends on. It depends on k1, k2, k3, k4, and also the k of the intermediate guy, right? Now, so I have k1 plus k2. Let's call that k intermediate. And so it's also going to depend on the magnitude of k intermediate. Okay? A general 4-point function could depend on, well, we might say a little bit, we'll do the general counting later, but this depends on only these lengths. All right, so let's write down the integral then. I have some eta and eta prime. So this is just the integral. Now we're in de Sitter. Okay, so what do we get from the Lagrangian? So remember, from the root g's, we get a d eta over eta to the 4th. And then we get a d eta prime over eta prime to the 4th. But now, what is this propagator? So let's remind ourselves, what is this propagator? The classical solution here was eta, e to the I, k eta. Okay, so that's the propagator now divided by eta naught. Okay? So first of all, I'm going to get an overall 1 over eta naught to the 4th. So let me put the eta naught to the 4th out in front of this thing. So from now on, I'll just talk about the thing with the eta naught 4th in front of it. Then I have so I have 2 propagators on the eta side. So there's an eta squared, e to the I, k1 plus k2. Eta. Then I have eta squared to the I, k3 plus k4, eta prime. And then I have this bulk-to-bulk propagator, g of eta and eta prime. let me call this, the 4-point function itself, f hat, so this combination I'll call f. Okay, so am I writing big enough, guys? Okay, so f is equal to no. Okay, thank you. Is that you, Spenta? Is this better? And I'm just going to abbreviate K12 for the sum of K1 plus K2. And I'm deliberately not writing this explicitly. Let's just remember what it is, right? That's supposed to be, this is a theta of eta minus eta prime, and then we're going to have Hankel, right? So there's some Hankel negative K eta 2, Hankel negative K eta prime 1, and then there are going to be other pieces. So there's some Hankel stuff in here, okay? Now, so now you see why this calculation looks tough, because I have to do this integral with 2 Hankel functions multiplied together, and I have to integrate from minus infinity to 0. Okay, now your best strategy for doing integrals is to give it to Mathematica. Mathematica doesn't know how to do these integrals, and you try very hard. You look around, is it some special function? This is nobody's special function, okay? This integral does not have a name, it's nobody's special function. And so our goal in this lecture is to calculate it, okay? And we'll find out what it is. Maybe after this lecture it can be called the ICTS special function, okay? But I want to stress, this is what we get from the standard time bulk representation, right? That's what it looks like. All right, so that's going to be the star of the show. We're going to try to understand it. Now, we're going to just do very, very simple things. There's nothing particularly that I'm doing here is there's nothing especially deep going on. But as I mentioned in the first lecture, the attitude we're going to take is that this is, after all, some function in the end of K12, K34, and K intermediate. Sorry, I should have said here, this G also depends on K intermediate. And we're going to try to take the attitude of figuring out, directly. Imagine we're just living on the boundary, right? We just have these things that depend on these 3 variables, K12, K34, and K intermediate. What property of this answer, what are we looking for in this answer that has the imprint of the fact that it came from time evolution in this way, okay? So what we're going to very shortly do is see that this thing satisfies a differential equation. It satisfies some interesting differential equations on the boundary that are really keeping track in a very precise way of the time evolution in eta and eta prime separately, okay? We're going to derive that differential equation, and then we're going to forget about this integral. We're going to spend the rest of the lecture solving that differential equation, and seeing how that beautiful little differential equation spits out all of the physics that we associate with time evolution, including particle production, all those things that we talked about from a purely boundary point of view. Okay, so that's our goal for this lecture. Yes. Yes. No, sorry. Thank you very much. Thank you, Logan. The scalar is conformally coupled, its mass is conformally coupled, the interaction is not conformal, okay? So the answer is not the same as in flat space. Now, had we made sigma also conformally coupled, so if the mass of sigma is conformally coupled, then it would be, okay? Then these Hankels would turn into another eta, e to the ik eta, and this would turn into one of the calculations that we just talked about. But we're going to imagine a general mass, in fact, a big mass, okay? So where the things are most interesting. Okay, so yes? Well, if I quote Nati from earlier lectures, there's no such thing as general coordinate variance. But a little bit less jokingly, that's not any different than I mean we're choosing coordinates to do a calculation. General coordinate variance is simply the freedom to choose other coordinates if we wanted to. But we'd all agree, and we'd get exactly the same answer on the boundary. Okay, so now let's just first clean up some things on what you could call units. All these things, there's Hubbles that have taken everything into account already, but still there's some overall scaling with these K12, K34, and K intermediate. So let's just take care of that quickly. For example, remember that G, and I'm going to write down the differential equation that G satisfied. So K intermediate squared, that was the vector K1 plus K2, all squared. And this was eta to the fourth delta of eta minus eta prime. So you see, everything here almost depends, all these things are dimensionless. Everything here depends on the combination K intermediate, except here. So if I put a, let me just call that K for now. If I call this K eta to the fourth, and I put a K here, then I would have to normalize that by putting a 1 over 8 K cubed. And therefore, G of K and eta prime is just 1 over K cubed times some other G, we just call it G hat, of K eta and K eta prime. Okay, so that just depends on the combination K eta and K eta prime. And therefore, I can also trade the eta and eta prime for K eta and K eta prime. And so what I'm left with is this F is an integral with just a 1 over K intermediate in front of everything. An integral, let me call it d eta hat over eta hat squared, d eta hat prime over eta hat prime squared. And then I have e to the I K12 over K intermediate, eta hat, e to the I K34 over K intermediate, eta hat prime, G of eta hat prime. Okay, so we see, where eta hat is K eta, K intermediate eta hat prime is K intermediate eta prime. Okay? Sorry? Oh, sorry, this was the G hat. Thank you very much. Okay, so we see that the whole thing scales with a 1 over K intermediate in front of the whole thing. All right, so now what is our, yes? Sorry? No, because it's the magnitude of the vector. Okay, so is that clear? Okay. Okay, so now what is our strategy? Well, we know that G satisfies this differential equation in eta dd eta, but because G essentially almost only depends on eta via K eta, then clearly we should be able to trade derivatives with respect to eta with derivatives with respect to K. So that's what we're going to try and do. Okay, what we want to do. So in other words, if I draw a picture, I had this thing. Of course, only the sum mattered. I have my propagator. I have this. What I want to do is I want to. I know that if I hit with some roughly speaking, if I hit with the differential operator box there, then I greatly simplify the problem. I collapse this to a point. So what I'd like to do is find some way of hitting some operator up here, such that the operator up here, acting on the external guys, turns into this box operator acting on the internal one. Okay? Now that's very simple to do. Let's just do some small manipulations. So you see, just our strategy has to break the symmetry between one side and the other, right? This is a derivative with respect to one time or the other time. So I have to break the symmetry between one side or the other. So I'm going to choose to define this operator just acting, let's say, on the 1-2 side. Okay, so remember, my F is 1 over K intermediate times something that I can call curly F that just depends on K12 over K intermediate and K34 over K intermediate. And this curly F, just this curly F, was the thing whose expression we just wrote down. Okay, well, it's just here. Okay, so actually, let me just put it over here. If I multiply this by K intermediate on the other side, so this is K intermediate F. Let me define that for the moment to be this curly F, which only depends on these ratios. Sorry, I'm not writing big enough. Okay? But what I want to do is, since I want to hit a derivative with respect to eta, I've done too much now. I can't access eta, so I'm going to undo this change of variables that I did here, and I'm going to go back to eta variables just for eta, but leave this as eta hat. Okay? So if I do that, this is just equal to 1 over K intermediate again, just from the change of variable here, and integral d eta over eta squared, but the rest is the same. D eta hat over eta hat prime squared. This is going to be back in e to the I K12 eta, still in e to the I K34 over K intermediate eta hat prime. And this G hat now depends on K eta hat, K eta and eta hat prime. And now we're in business. Now we're in business. Now let me look at K intermediate times curly F. Okay? I want to take that out here. So I'm looking at K intermediate times curly F now. K intermediate curly F. Let me put it over here. K intermediate curly F is now going to satisfy an interesting differential equation. So if I look at K intermediate squared, D squared K intermediate, minus 2 K intermediate, dd K intermediate. Okay? Now, what is that going to do? Precisely because these only depend on the combination K intermediate eta, this is going to act on the inside exactly as eta squared minus 2 eta dd eta. Okay? So we've got that part of the differential operator. What about this one? I need to pull down an eta squared. How do I get an eta squared? Eta squared is just negative d squared by dk12 squared. Okay? So I get negative k intermediate squared, d squared by dk12 squared, then just positive m squared, k intermediate f. Right? So now, what has that done? This has come into the integral and precisely turned into our differential operator on g hat. So that hits g hat and turns it into the delta function. So let's see what we have left. This is equal to the integral. Yes? Sorry? No, sorry. I'm thinking of this as an independent variable now. Okay, so I'm thinking about K34. I could have called that K34 hat. Okay, so sorry. Thank you very much. So I'm thinking of this variable as being held fixed when I do this computation. After all, these are the things that it depends on up here. Okay, thank you very much. So this is fixed. Okay. So what I'm left with is d eta over eta squared, d eta prime over eta prime, d eta over eta squared, d eta hat over eta hat prime squared, And the delta function was just k intermediate I get k intermediate eta squared, eta hat prime squared, delta of eta hat prime minus k intermediate eta. And that's what I got from the delta function. And so you see there's an eta squared, eta prime squared. These things go away. I'm left with my integral e to the I k12 eta e to the I k34 over k12 eta hat. And so this is just equal to k intermediate squared over k12 plus k34. Just doing the integral over time. All right, so, but again, this is nothing other than what we get after, just loosely, after we collapsed the intermediate propagator. Okay, yes? Yes? They didn't turn it. That's the whole point. We just found a differential operator on the outside that detected the time evolution on the inside. Okay? Oh, that's sorry. No, eta dda is the same as k ddk because these things only depend on the combination k eta. Okay? Yeah, that was the trivial part. This part was slightly more interesting, that we managed to get the eta squared, k intermediate squared in this way. All right, so let's summarize. So in summary, we have this differential equation, k intermediate squared, d squared k intermediate, minus 2k intermediate, dk intermediate, minus k intermediate squared, d squared k12, plus m squared on k, this f, this curly f, is equal to k intermediate squared. Let me write it as k intermediate times k intermediate over k12 plus k34. Okay? And so now I can, because I know that f only depends, so now let me say that f is really a function of what I'll call u and v, where u is k intermediate over k12, that'll be slightly more convenient, and v is k intermediate over k34. Right? We know that curly f is just a function of those dimensionless ratios, so let me just put that in. I'm inverting it. Why am I inverting it? Because if you remember from the first lecture, we're interested in the limit. We're interested in these squeeze limits, where two of the sides become very long and one is short. I want that limit to correspond to u goes to 0, and v goes to 0 rather than infinity. It'll just make it a little easier. Okay? So, if we do that, this differential operator turns into some differential operator in what? In just u. V is fixed here. Right? But the right-hand side will depend on u and v. And so, just a short exercise. I won't do the algebra for you in real time, but let's write down what the final answer is like. Is u squared, 1 minus u squared, u squared, minus u cubed du, plus m squared minus 2, f of u and v is equal to 1 over u plus 1 over v, that's the k12 plus k34, which is uv over u plus v. I'm sorry. Yeah, this is the only m we're going to have from now on, so I hope I don't keep slipping. But okay. This is the mass of the signal particle. This is the mass of the heavy particle. Now, if you remember our relationship, our object little mu squared, which was m squared minus 9/4, in terms of mu squared, this is also mu squared plus 1/4. So I'll actually probably switch to that notation. Okay, so notice there's something quite remarkable about this, right? This is an ordinary differential equation in U. It's a function of U and V, right? But it satisfies an ordinary differential equation in U. It's inhomogeneous, the right-hand side depends on V, but it's an ordinary differential equation in U. And ODE is keeping track of, so it tells you, I fix V, so I have my 4-point function, I have my sides K1 and 2, and I make those sides longer and longer and longer, keeping this side fixed. Okay? So I make the 1, 2 sides longer and longer and longer, and that satisfies an ODE all by itself. Or I can keep these sides fixed, I can make the other sides longer and longer and longer. That satisfies another differential equation. That's a remarkable thing. If I call this whole operator LU, so this is something that looks like LUF is equal to UV over U plus V. And remarkably, exactly the same function also satisfies the same equation in V. There are two separate ODEs that the same function satisfies. Okay? So these are keeping track in purely boundary terms of the history in eta and the history in eta prime in purely boundary terms. See, we're used to the idea in inflation that the overall time in the bulk, or in ADS, CFD, that the overall time or the location of the bulk is given by overall scale on the boundary. That's fine. Okay, that's the scale symmetry, which is. But here is something much more detailed, right? Here we're seeing the actual history for what gave rise to this 4-point function, as seen from the perspective of one time or of the other time. And of course, what's non-trivial is that there has to be a consistency between them. Okay. So. Now, here we derive this differential equation beginning from the bulk perspective. Towards the end of the lecture, I'll tell you how we can arrive at these things without ever talking about the bulk. Okay, and that's the analog of what I was talking about in the first lecture for scattering amplitudes. How we can, just by making some simple assumptions about what the analytic properties of the object are and using invariance, we can figure out the structure of the amplitudes that we're looking for. There's an analog of that we can do here involving the conformal symmetry of these correlators on the boundary. But for now, we got them anyway, and now we're going to study these differential equations. But what I want to say is that from this differential equation point of view, it is not obvious. So it's kind of cool that there's this ordinary quote-unquote time evolution by making these set of sides long, or the other set of sides long. But if I started from this point of view, it is not obvious that you could find a consistent solution, that the two histories could be consistent. That's what the bulk representation is making manifest. Okay, so the one thing the bulk representation is good for, it's lousy for doing any calculation. We'll see, you just stare at that, the blue in the face, and you'll never compute it. We're now going to compute it starting by solving these differential equations. But one thing the bulk makes manifest is that these times pictures are consistent with each other. All right. Yes, any questions? Yes. Yes, that's what we'll spend a lot of time talking about in the next lecture. Not really, well, yes, we can. I mean, I'll be doing some general time-dependent problems in the next lecture, but yes, absolutely. And an application of all this formalism is just calculating the vacuum wave function in flat space. Okay? Okay, any questions? All right. So let's first calculate in the sort of simplest way we can. I mean, imagine the mass of the particle is big. Okay, so then we can do the sort of standard effective field theory type of calculation. In this case, we're just inverting operator LU, but it has a big mass sitting there, so we can invert it perturbatively in U. Perturbatively in mu, sorry. Okay, so let me write LU, or V, is some delta U, or V, plus mu squared plus a quarter. Okay? And so clearly we can, clearly I can write F is equal to UV, well, equal to 1 over mu squared plus a quarter, and then 1 minus delta U over mu squared plus a quarter, plus delta U squared, mu squared plus a quarter squared, plus dot, 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 just formally inverting, acting on UV over U plus V, right? So that's the, I'm just inverting the operator, right? So that's the, and just expanding it. So that's the formal answer, and this is giving me a power series in power of 1 over mu squared. So this is the effective field theory expansion. Already, there is something slightly remarkable here. Let's look at this first correction. So the leading term is symmetric in U and V. That's good. The function should be symmetric in U and V. But let's look at the first correction. This is just a delta of U. It's not obvious that that's going to work. It's going to do something nice. However, I'll just leave a tiny exercise in typing in Mathematica that delta U of UV over U plus V is actually equal to negative 2 U squared V squared 1 plus UV over U plus V cubed. Again, it's beautifully symmetric in U and V. Okay? Okay, so quite beautifully, delta U minus delta V annihilates UV over U plus V. Okay, that's slightly non-trivial. And because of that, so does this for any power. Because the operators commute, and I can just factor as delta U minus delta V times sum of a bunch of other stuff. All right? So that means, quite beautifully, to all orders in the effective field theory expansion, we have perfect consistency. Okay? And despite the fact that we have two different histories, we are computing exactly the same object. So that's the first thing that we've done. So we've computed F in the effective field theory approximation in U is equal to F in the effective field theory approximation in V. Good. The two histories are consistent. However, this can't be the full solution. Okay? And the physics of why this can't be the full solution is, again, exactly what we discussed qualitatively in the first lecture. There's particle production. We should be seeing these oscillatory pieces. Okay? This is perfectly analytic. As U and V goes to 0, these are perfectly analytic. That's exactly as we said in the first lecture, in the effective field theory approximation, you don't see particle production. They're non-perturbative in mu corrections to these formulas that we're missing when we do that naive inversion. Okay? When we write down 1 over the operator, that's formally correct, but then we're assuming that we can do a power series expansion in 1 over mu, which is incorrect. Okay? And we'll see that there is non-perturbative exponentially small contributions, and we're going to look at calculating. Okay. But before doing that, let's try to get an idea of how to solve this equation. After all, we just have some second-order differential operator with an inhomogeneous source term. So the other obvious thing we should do is look at what the homogeneous solutions look like. Okay, so let's look at what the homogeneous solutions of this differential operator look like. So that's the little slightly scary-looking differential operator. So let's write it down and stare at it a little bit. All right, so we want to look at the homogeneous solutions of delta U plus mu squared plus a quarter little f equals 0. And I'll write the whole thing down again. U squared 1 minus U squared, U squared minus 2U cubed du plus U squared plus a quarter. F equals 0. Now, which one of you guys is afraid of the differential equation? Okay. Definitely afraid of this differential equation. But you don't need to be afraid of any second-order differential equations ever. Okay? And there's a good reason for this. If you have second-order differential equations with rational coefficients, I mean, if there are some logarithms out front, then I'd be terrified. Okay? But if it's a second-order differential equation with rational coefficients, then you can always write it in a way where it's d squared, and then you have some polynomials downstairs, and downstairs in front of the other coefficients. And there's a general theory that was developed in the 1800s for what the solutions of these differential equations look like, period. All that matters is seeing how many singular points the differential equation has. Okay? Now, if it has up to 3 singular points, the differential equation has up to 3 singular points, then any differential equation, any second-order equation with 3 singular points is a hypergeometric function. That's a definition of a hypergeometric function. Okay? The hypergeometric equation is a particular second-order differential equation. That particular second-order differential equation is just putting things in a canonical place so the singularities take place at 0, 1, and infinity. But if you have a random second-order differential equation with singularities anywhere, just by doing a change of variable, you can always push it anywhere you like. You can push it to 0, 1, infinity if you like, and then it's guaranteed to be a hypergeometric function. That's why hypergeometric functions are everywhere in physics. Okay? Because typically the most complicated thing we do involves not too many singularities. Okay? For example, you could try to keep going and ask what's the most general solution of a second-order differential equation with 4 singular points. Those are called Hume functions. But anyway, it starts getting boring after that. Now, once again, as I mentioned for the Bessel functions yesterday, what's special, and the reason why great mathematicians were involved with this and not just, mirrors, is what's special about, no offense, okay? That was really, sorry about that. Is that what's very non-trivial is that we have singular points. In the neighborhood of any of those singular points, the whole point is that you have solutions that just look like simple powers, or perhaps logarithms if it gets a little degenerate. So you have solutions that are well behaved around the singular points, but then the magic, just as we saw with the Bessel function, which is a special case of a hypergeometric function, the magic is that we know if I take a solution which is well behaved around this singular point, how do you expand it as a linear combination of the solutions that are around the other ones? Okay, and there's a whole story of how that works. Anyway, that's why you don't have to be scared. If you see any second-order differential equation, all you have to do is look to see if it has how many singularities it has. If it's up to 3, you're cooking with gas. Okay? All right, so where are the obvious singularities of this differential equation? There's an obvious singularity. U goes to 0. There's an obvious singularity as U goes to 0, right? The coefficient of the second-order derivative cancels. There's another obvious set of singularities as U goes to plus or minus 1. So there's 3. We have to check infinity, though, as well. So let's say we send U to infinity. So let's say I send U to 1 over W and send W to 0. Then actually think wonderful, because as U goes to infinity, this thing is U to the 4th du squared. And U to the 4th du squared is, in fact, nothing other than dW squared. So this is perfectly non-singular. Okay? So there's no singularities other than at 0, minus 1, and 1. So it's a hypergeometric function. Right? But before saying what hypergeometric function it is, and by the way, if you ever encounter this, of course, you can also just shove it into Mathematica and it'll tell you. But if you ever encounter it, all you have to do is you take your equation, whatever form it's in, you see what the powers are of the solutions in the neighborhood of the singularities, which you can work out. That's the whole point. The differential equations simplify in the neighborhood of the singularities, and then you're done. And then all you have to do is do the SL2 transformation that maps your points to 0, 1, infinity to know which hypergeometric function it is. Right? So it's very simple. But let's actually take a peek at what the singularities look like for us without. So that's an obvious thing to do. So let's first look at the singularity as U goes to 0. Okay? So that's the one which, again, that's this squeeze limit that we were talking about. Here. Okay. So as U goes to 0, well, we can drop the U to the 4th pieces, and this differential equation becomes very simple indeed. It's just U squared plus mu squared plus a quarter f equals 0. And you can solve this very trivially, of course. But I so I'm going to just do this just because I think it's a good habit to get into. Whenever you have something dimensionless like this, it's always useful to introduce that dilation operator. Okay? So in terms of that dilation operator, this becomes that capital D squared minus D, which is minus a quarter plus mu squared plus a quarter. So you see very nicely those quarters canceled on little f equals 0. And therefore, it's the dilation operator minus the half squared plus mu squared f equals 0. Therefore, f equal to u to the half plus or minus I mu. Okay? So those are our friends, the oscillating solutions. Okay? And then I'll work out for you to work out that the singularity as u goes to 1, that what the two solutions look like. It's a slightly degenerate case, but I can have solutions that just go like a constant, or I can have solutions that look like b plus c log 1 minus u. So there's a logarithmic, there can be a logarithmic singularity as u goes to 1, and then similarly for u goes to minus 1, something similar. Okay, so those are what the three singularities look like. As u goes to 0, oscillatory with a half plus or minus I mu, and we get these logs as u goes to 1 or minus 1. And that's it. When you know all those powers, you're done. You know what the powers look like in the neighborhood of the singularities. You know what the singularities are. You know what the hypergeometric function is. Okay? Well, that's what we saw in the first lecture. Those are what, this is u goes to 0. Okay, and this is something that corresponds to this is the squeeze limit, and the oscillations are the oscillations we talked about last time. Okay? Actually, sorry, thank you. You actually, I meant to do this right in the very beginning of the lecture, but since you asked about it and I forgot to do it, I have twice written down an incorrect formula for the 2-point function involving the massive particle in flat space. I was rushing toward the end of last time, so let me actually write it down correctly. Sorry, this is going way back to the last lecture, but it's just reminding us what these oscillations have to do with. But so this is just an aside. So that 2-point function for the massive particles in flat space is the oscillatory piece is actually 1 over mu 1 over x minus y cubed. And then I have a cosine not of m times, it's a cosine m over Hubble even. Well, I'm working units with Hubble equal 1. Not of x minus y itself, which would be what's in flat space, but the log of x minus y. There's a log of x minus y over some IR cutoff. And this is very important. It's very importantly related to what I was saying also about the result not being exactly scale invariant and so on. But remember, this is something that was coming. This was something that was coming from a negative k eta to the 3 halves plus or minus I mu, right? So we have a k eta naught. So there's some. It remembers where eta naught is. Okay, that's sitting here in this IR cutoff. So. Now, the physics is the words that I was saying. I just wrote down the wrong formula. It's just that this is the dilution by the expansion in the universe, but in inflation, the universe is expanding exponentially. This is cosine mass times time, okay? But the distance is exponential in the time, so that's why there's a logarithm there. Okay? All right. Sorry? No, it is not. They have nothing to do with each other. In fact, I'm going to come, getting rid of this singularity is going to play a role in determining the answer, okay? So this is this squeeze limit as u goes to 0. So these oscillations here are the oscillations we saw before. The only difference is that here there's a 1/2 plus or minus I mu. In our discussion last time, there was a, well, yeah, so, yeah, no, never mind that point. The important point is the oscillations are the same as the oscillations we're talking about. All right. Thank you for asking the question. Sorry about the aside and that I didn't do it earlier. Okay. Okay, so we can then write down what the answers are, and what I want to do is write down answers for the solutions of the homogeneous equation. Remember now that are the ones that are nicely behaved as u goes to 0. So with the plus sign and with the minus sign there, and so this is what the full solutions look like. The F is these are convenient prefactors. They don't matter that much for our discussion. And as you'll see, we're not going to need any of these details except for one little point, but it's a hypergeometric function, f21 of a quarter plus or minus I mu over 2, 3/4 plus or minus I mu over 2, 1 plus or minus I mu, and u squared. Okay, and again, I just want to point out that whenever you get these things, you get some hypergeometric thing, there's always these funny-looking arguments in here, right? That's simply the fault of the hypergeometric. That's simply the fault of the way the hypergeometric equation is normally presented. In fact, there's a more symmetric and beautiful way of talking about all those equations, slightly more symmetric and beautiful, that are associated with the name of general Riemann symbol. So Riemann just worked out just the story without doing the SL2 gauge fixing, if you like, to send points to 0, 1, and infinity. And so in that form, you literally just say, oh, the singular here, there, and there. You write down the powers, tuck, 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 and you're done. Okay? That's what Mathematica is doing when it spits out the answer. Okay? So the reason for those funny things is simply the artificial bringing it back to a form. I mean, that's just the labeling. You back to the form where you put the singularities at 0, 1, and infinity. Okay, now, the main thing that's going to matter for us, the detailed form will not matter, but the main thing that will matter for us is, as we saw, again, the same story again and again, is that that's f plus or minus. The main thing that matters is that we also know the behavior of f plus or minus in the neighborhood of the singularity as u goes to 1. Or minus 1, but we'll just keep track of the 1 as u goes to 1. F plus or minus goes to some either alpha, if it's plus, or a complex conjugate of this number alpha, if it's minus, times log 1 minus u. So it has that singular behavior, both of them. Okay, where alpha is a specific number. Alpha is gamma of 1 plus I over gamma of a quarter plus I halves, gamma of 3/4 plus I halves. But it's just a specific number. It's around 0.1 plus 0.4 I. Okay? So these are the homogeneous solutions. Okay? These are the homogeneous solutions that are well behaved with oscillatory behavior, and they all also have singularities as u goes to 1. All right. So now let's move on to solving this differential equation. Okay, so we just want to find the most general solution to this differential equation. And we know the solution to the homogeneous equation, so all we have to do is find a particular solution. Okay, so that's what we're going to do, is concentrate on finding a particular solution. And it's also clear, by the way, that effective field theory answer, the effective field theory answer is going to be pretty close to the right answer, right? We're expecting exponentially tiny corrections associated with it. That effective field theory answer has the property that it's analytic as u goes to 0, as v goes to 0. So let's look for a solution that's analytic as u goes to 0. So I want to find a special solution of the inhomogeneous equation that's analytic as u goes to 0. before looking at the totally general problem, I want to simplify this differential equation by looking at a limit first. Okay, so this is going to be a simple limit first, where we'll have a lot of fun. Remember, we have delta u plus mu squared plus a quarter f equals uv over u plus v. This damn source is all the problem, right? If we didn't have the source, we just have the hypergeometric stuff. So let's make the source small. I'll make the source small by making v small. Okay? So I'm going to make v small, but I'm going to scale u with v. So I'm going to say u is x times v. And I'm going to write f itself will look like v times some f hat. And then in this limit, the differential equation just becomes x squared dx squared plus mu squared plus a quarter f hat is equal to x over 1 plus x. Once again, this is just dx minus a half squared plus mu squared f hat equals the same thing. And therefore, if I further scale, f hat is root x times, let's say little f. And for the moment, I put x is equal to e to the t. Then this is just a forced harmonic oscillator. Actually, let me put it here, put it in the central spot. And I just have dt squared plus mu squared little f is equal to 1 over e to the t over 2 plus e to the negative t over 2. Okay? So this is just a forced harmonic oscillator with a particular forcing term, right? It's 1 over cosh t, so I'm giving it a gentle kick and speeding up and then slowing it and then stopping kicking it, right? And so there's a solution of this. Now, just here, we can solve this problem exactly, except what does it mean solve it? Because we can invert, we can solve this problem exactly. And you can write the answer in terms of some hypergeometric functions, okay? So little f is actually, in this case, it's solved by some hypergeometric function. So this is another example of what I was saying, this general comment I was making yesterday. Here's an example. If you give that equation to Mathematica, it would solve it. It would tell you it's a geometric function. You could play with it. Actually, it wouldn't tell you. Mathematica is very stupid about solving equations. But anyway, after some manipulation, you could, Mathematica is really only good for manipulating rational expressions. That's just the word to the wise. If you want to integrate anything, use Maple. But it's some hypergeometric function. Oh, we're done. I have the analytic solution. We're done. But you see, you're not done. KAWS and those guys were done, okay? Because they figured out all the limits, how everything worked. And that's why it's going to pay for us to figure out those things for ourselves, just in this example, because later for the full problem, it doesn't have a name. So we have to do it. Okay? So let's already see and understand how it works in this example. Okay? So despite the fact that it has an analytic solution. Okay. Now, I want to make a few obvious comments about this. This obviously has a t to negative t symmetry. Okay. And let's do the same things we're talking about. Let's first look at the effective field theory solution is. In other words, just as the naive inversion. Sorry? What is t? Oh, sorry, x was e to the t. Okay? Yeah, sorry, I apologize. So x was e to the t. I'm sorry if I'm not writing big enough. Okay? All right, so again, the effective field theory solution is just little f is 1 over mu squared, 1 minus dt squared over mu squared, plus dt to the fourth over mu squared plus dot dot 1 over e to the t halves plus e to the negative t halves. So again, this is perfectly fine. It's nicely behaved as t goes to plus or minus infinity. It's symmetric, obviously symmetric, and t goes to minus t. Okay. So let's just solve this. Let's just solve this differential equation in a power series in x as x goes to 0. So as time goes to minus infinity. So in order to do that, so I'm just going to expand 1 over e to the t halves plus e to the negative t halves is e to the t halves 1 minus e to the t plus e to the 2t plus dot dot dot. Okay, remember, t is going to minus infinity here, so this is all going to 0. And let me put f itself, let me expand f is e to the t halves, so clearly there's going to be e to the t halves, c0 plus c1 e to the t plus c2 e to the 2t plus dot dot dot. And then the differential equation dt squared, then just the differential equation then just tells me, so dt squared plus mu squared f equals 1 over the negative t halves, then just tells me an equation for these coefficients. Okay, I just learned that n plus a half squared plus mu squared Cn equals minus 1 to the n. Okay? All right, so I found a solution. So I know what these coefficients are. I'll write it down in a second. But let me give this solution a name. This is a solution of the differential equation, which is analytic as x goes to 0. And never mind the overall e to the t halves out in front. Okay, but it's a solution that's well behaved and analytic as s goes to 0. Yes? Yes, I already took that out. This is for little f. So in fact, if I added that root x back, it would even remove that little non-analyticity in that little root x. Okay, but I'm gonna leave it here. I'm not gonna multiply by that. The calligraphic x is completely, totally analytic. It doesn't have it does not even have a square root in it. Okay. But I'm taking it up here for a reason that'll become, yeah. Sorry? No. This is not that root x. This is just the fact that solving this equation, like, look, the like leading term would look like 1 over mu squared e to the t halves. Okay? What I was saying is that it might bug you that there's this little non-analyticity in x here. There's something that looks like root x, but for the full answer, there's a root x in front of everything. Okay, so that takes care of that guy. Okay, but I'm doing it like this. It'll be slightly more convenient for me. All right, so let's call this solution. So there's a solution. There's a solution of the equation of motion. Oh, sorry, there's a solution of the whole equation, which is analytic up to that square root factor, but anyway, which is analytic as x goes to 0. Let's call that solution f minus of x, right? And we've just figured out what f minus x is. It's the sum over n minus 1 to the n over n plus a half squared plus mu squared x to the n plus a half. X was e to the t, remember. All right? Now, this was a solution that was developed as a power series around x equals 0. Okay, so let's look at it and see how far we can extend that. So this guy has obviously, if x is bigger than 1, we're screwed. If x is less than 1, we're totally fine, right? There's 1 over n squared here. It's totally convergent. Okay, so this is a solution that's valid when x is less than or even equal to 1. I can take it all the way to 1, and it's still perfectly convergent at x equals 1. Now, notice, parenthetically, I'll just say, this will be important in a second, that even f prime of x, one derivative, okay? Now, one derivative pulls down one more power of n, so it's the sum of a 1 over n, but with alternating signs, okay? So this is also perfectly okay up to x for x less than or equal to 1. So it's convergent even at x equals 1. That'll be important in a little bit. Okay, but what I want to emphasize, this is not the definition of this function, right? I mean, this is, well, the function has a finite radius of convergence. So I haven't told you anything about what it looks like outside. This is just telling us that the solution of the equation, which is analytic for x close to 0, looks like this when x is smaller than 1. And we have no idea what it looks like yet for when x is bigger than 1. So that's what we'd like to figure out. We'd like to extend the solution to something that makes sense for x bigger than 1. Okay, well, how do we do that? Well, let's first write down the other obvious solution, which is analytic around x goes to infinity. Okay, so we have a solution analytic around x goes to infinity, which is f plus of x is equal to the sum over n minus 1 to the n over n plus a half squared plus mu squared, x to the minus n plus a half. And this is valid when x is greater than or equal to 1. Yes? I apologize. I should have learned from Fernando yesterday. Okay? You can only try to copy Fernando so much. Is that good enough? You sounded unconvinced, actually. All right, and this is valid for x greater than or equal to 1. All right, now we have two solutions of the inhomogeneous equation. Therefore, their difference must be a solution of the homogeneous equations, right? So let's look at that. Let's look at f plus of x minus f minus of x. Now, you see, this is guaranteed to be some solution of the homogeneous equation. So I can write it as, and the solution of the homogeneous equations are e to the I mu t, e to the minus I mu t. So let me write it as, which is x to the I mu and x to the minus I mu. So let me write it as a plus x to the I mu minus, that minus sign will be convenient, a minus x to the minus I mu. I don't know what f plus and f minus are. I don't know, now I want to figure out what a plus and a minus are. But this guy, I only have a formula for when x is less than 1. This guy, I only have a formula for when x is bigger than 1. But I can match these expressions exactly at x equals 1. Okay? So this expression, as well as, let me take its derivative. F prime of x minus f minus prime of x is equal to I mu a plus x to the I mu plus a minus x to the minus I mu. Okay, so from the first equation, I conclude that these two expressions are equal at x equals 1, right? So I have to have a plus equals a minus. So if I evaluate these guys at x equals 1, I learn that a plus minus a minus equals 0. And from here I learn that 2I mu, so let me, sorry, a plus minus a plus equals a minus, so let's call that a. And then from here I learn that 2I mu a is equal to f plus prime minus f minus prime, which is the sum of 2n plus 1, so that's n plus a half minus n plus a half, a minus sign out in front, minus 1 to the n over n plus a half squared plus mu squared. So it's just a number. It depends on mu. It's a function of mu. And I hope you all recognize this as pi over cosh pi mu. Okay? So to recognize them as the same thing, thought of as a function of mu, you just have to notice that they have exactly the same poles and residues at the poles. Okay? The residue at the pole is when mu is equal to an integer, mu is plus or minus a half integer, and you can just work out that the residues are exactly the same. Okay? So the residues for both, as mu goes to m plus or minus I m plus a half, is minus 1 to the m for both of them. All right. So you see, that's cool. This is something that's non-perturbatively small in mu. Okay? At large mu, it goes like e to the minus pi mu. And so that's great, because now we're done. Now that we know what the difference between f minus and f plus are, we can extend, let's say, f minus everywhere. So we have a nice formula. So f minus of x equals plus of x plus pi over cosh pi mu, x to the I mu minus x to the minus I mu over 2I mu. And hence, we have a formula for f minus of x equals the sum of minus 1 to the n, x to the n plus a half, which is valid when x is less than or equal to 1, but a sum of minus 1 to the n, x to the minus n plus a half, over n plus a half squared, plus mu squared, plus pi over cosh pi mu. That's valid for x greater than or equal to 1. Okay? And so we're done. That's what now, what is the physics of this? We had a harmonic oscillator. It was in its classical, so it wasn't moving, not even a ground state. It was just sitting there. I kicked it with this gradual 1 over cosh t kick. The whole thing was quite adiabatic, a very heavy oscillator. Whole thing is very adiabatic, so mostly it goes up and comes back down, but on the other side, it's oscillating a little bit. Okay? And so that's exactly what we see. Right? Notice that while to every order in 1 over mu, f minus had a t to negative t, or x to 1 over x symmetry, the full exact answer, the e to the minus pi mu corrections spoil this. All right? So let's say you want a solution. Let's say you want a solution that has the x to 1 over x symmetry. What is that solution? I have to add a homogeneous solution of the equations to this one in order to enforce that symmetry. And so if you want that solution, we can call that f symmetric. So f symmetric in T is just equal to the sum over n, I won't keep writing that expression here, plus pi over cosh pi mu, x to the minus I mu over 2I mu. And here I have the sum over n of the thing with x to some powers, of x to minus those powers, plus pi over cosh pi mu x to the plus I mu over 2I mu. Okay, but you see something rather beautiful, that the only solutions, there's a conflict between the analyticity of the answer and the t to minus t symmetry. The only solution, which is symmetric, that has this symmetry of the problem, inevitably has to have these exponentially small oscillatory pieces at that. Okay? Any questions about this? Yes? No, this is not U and V exchange. This was this was just a feature of this equation, and it came out after I took out the root x and all of that stuff. Okay? We'll see it. It'll be closely related to U to V. Yes, it's basically that. Okay, but it's because x was U over V. That's right. Yes, that's right. Yeah, I'm sorry. Yes. All right. Now with this under our belt, let's go back to the full problem. Logan, I'm going to need like 10 minutes, not 15, but 10. In planning on time, I forgot about erasing Blackboard time. So, huh? Well, are you saying it's? Are you saying it's more or less? You're just a jerk, you know. Like, you could be sympathetic. You could say, "Yeah, it's really. I wish there was someone up here erasing the blackboard for you. That'd be so nice." But no, instead you tell me I'm malingering. Yes, should have budgeted that I didn't have quite enough coffee, perhaps. That's what you're saying. All right, well, just you wait. Someday our roles will be reversed. I'll remember this day. No, you and you will get none. All right. Okay. So let's go back to the full problem. So the analog so just as we just said, the analog before, so in our toy thing we had x less than 1. That's exactly u over v less than 1, so u less than v. Okay? And so what we can do is go back to that full differential equation and just do exactly what we did in the harmonic oscillator, just write down the solution that's a power series in powers of u and u over v. Okay? And I'll spare you it's a totally trivial calculation. It's just exactly what we did before, but now I just have a function of 2 variables. So let me call that solution f minus, and I apologize that I also use the f's or hypergeometric solutions. I hope it won't be confusing because one will depend on 2 variables and the other one will only depend on 1. So this is f minus uv. This is a solution of our whole differential equation. This is the one that's analytic as u goes to 0, okay, for u less than v. And this is given by now sum over n and k of some coefficient ckn, u to the n plus 2k plus 1, v to the minus n. Okay, so again, that's as promised. It's an expansion in u and the ratio u over v. Okay? So is that clear? This is a nice convergent expansion. Let me tell you what the coefficients are. Where ckn is just minus 1 to the n, n plus 1, n plus 2, n plus 2k, over n plus a half squared plus mu squared, n plus 5 halves squared plus mu squared, n plus 4k plus 1. Okay, so those specific concepts. Oh, by the way, I should have a tiny comment about the last solution will be true here too. The expression we gave for f minus, the one that looks like a power series around x equals 0, a power series at x around x equals infinity with this correction, that's a very effective solution as well, right? Because it's expressed in the neighborhood of every point as a highly convergent power series. If you actually want to get the answer, you just keep a couple of terms and it's just within a % of the answer everywhere, all right? And again, that's exactly, I'm mentioning because that's what the guys were trying to do in the 1800s with their differential equations. They didn't have computers. They wanted to be able to effectively compute them with power series everywhere. And that's why it was useful to figure out how solutions around one point expanded in terms of around solutions around the other point and so on. Okay? So it's both conceptually interesting and also practically useful. Okay? And the same thing is going to be true for our new ICTS function. Right? All right. Now, we also have a solution, f plus of u and v. That's analytic. And v goes to 0 for v less than u. Okay, I won't write it down, but it's exactly the same thing with the roles of u and v interchanged. And now we do exactly the same thing. We take f plus minus f minus. Okay, f plus minus f minus satisfies the homogeneous equation, and we match the two solutions and their derivatives at u equals v. Okay? And that allows us to determine what the coefficients are. And the final answer is that f minus of u and v is equal to the sum of ckn u to the n plus 2k plus 1 v to the minus n, or u less than v. The sum of ckn v to the n plus 2k plus 1 u to the minus n, plus a correction that is still pi over cosh pi mu. But now instead of having just those oscillatory things like we had in the harmonic oscillator, we're going to have f minus, these are those homogeneous hypergeometric function solutions, f minus of v, f plus of u, minus f plus of v, f minus of u. Okay? And the fact that this works relies on a slightly non-trivial identity now, because you see here there's something kind of cool that depends on v and u sort of factorized here entirely as solutions of the homogeneous equations also in v, despite the fact that we're solving the equation only in u. Okay? And that relies on a slightly interesting identity that I'll let you have fun playing with. It's the analog of a formula for cosh pi mu, but now it depends on k. So it's 2n plus 2k plus 1. So what we get when we get the difference of derivatives now, ckn for those coefficients that I wrote down there, but this is sum over n for fixed k. Okay? So k is fixed, is equal to pi over cosh pi mu. For all k. Okay? So that nice fact allows this factorization to happen. All right, so now, yes, sorry? How do I get that result? Well, you can derive it the same way we derived the cosh result. You verify that the residues match on both sides. But now the residue calculation is slightly more interesting now because you have many more factors, but it's a nice exercise. Okay, so I'll leave that as an exercise for you. All right, so, well, that's just what we're coming to. Okay, so we see again, we have the solution by this non-perturbatively small correction. It breaks the symmetry between u and v. That's one thing. Another thing, which is interesting, if you notice that this solution, which is analytic, the solution that's analytic this is a solution that's analytic as u goes to 0. As u goes to 1, it's forced to have a singularity. Okay? So let's actually see what does this F minus look like as u goes to 1. Okay? F minus as u goes to 1. Sorry. Let me look at the, yeah, that's right. If I look at F minus as u goes to 1, from the behavior I told you, that each one of these things goes like log 1 minus u, this actually goes to pi over cosh pi mu, f minus of alpha, f minus of b, minus alpha star, f plus of b, okay, times log 1 minus u. So it has a logarithmic singularity as u goes to 1. Okay, so the solution that's analytic as u goes to 0 is not symmetric, and it has this funny singularity. Now, that funny singularity as u goes to 1 is a crappy singularity. Remember, that's the kind of singularity that we also qualitatively talked about in the first lecture. What is a singularity as u goes to 1? So let me draw a picture of, I have a 4-point function, so I have k1, k2, k3, 4, but it doesn't matter where they are. So let's say here's k1, and this is k intermediate. So u goes to 1 is when k intermediate divided by the sum of those lengths is going to 1. That means that this triangle is collapsing. Right? It's like going like that. Okay? And the answer, there's a solution that has a singularity there, but that's a totally meaningless singularity, right? For example, you get a singularity where? Here, here, where on this line should the singularity be? Why should it be equal along the line? What property should it have, right? That's a totally unphysical, garbage singularity. The other singularities, where we made these sides long, okay, those had interpretation, but there should be no singularities here, okay? So there's two problems with this. The solution that's analytic, as u goes to 0, is not symmetric in u and v, and it has a bad singularity as u goes to 1. So we have to add homogeneous solutions to the differential equations and see if by adding homogeneous solutions we can restore the symmetry in u and v, and we can remove the bad singularity at u goes to 1. And it's a totally trivial exercise. You just write down. We just take down, for example, f minus plus the most general thing we can do, a f plus of u, f plus of v, plus b f plus of u, f minus of v, plus c f minus of u, f plus of v, plus d f minus of u, f minus of v. And we just demand these properties and an obvious reality property that I won't explain, but it's just trivial algebra, and we get the final answer. So there is a function that satisfies all these properties. Okay, we can make it symmetric, we can remove the singularities at u goes to 1, and therefore also at v goes to 1, because we've made it symmetric in u and v. And so we have the final answer, the function that's symmetric, and no bad singularities of u and v is equal to the sum of ckn u to the n plus 2k plus 1, b to the minus n, plus, and it's the following cool thing, pi over 2 cosh pi mu f minus of u, f plus of v, minus f minus of u, f plus of v, plus alpha star over alpha. Remember, alpha was that number that we got from the coefficient of singularities, f plus of u, f plus of v, minus alpha over alpha star, f minus of u, f minus of v. Okay, so that's what the solution looks like. This is what it looks like when u is less than v, and just flip u and v when u is bigger than v. and swap u goes to b when u is bigger than. Okay, so that's the full answer. Yes? Sorry? No. We have to choose A, B, C, and D. Choose A, B, C, D, so that the answer is symmetric in U and V, and you cancel the singularity. Okay? Yes, and you see how it's going to work, right? So for example, choosing it, so this thing has to have an antisymmetric part in U and V in order to cancel the antisymmetric part in the subtraction there. And also, as U goes to 1, well, that looks like some combination of F plus and F minus times log 1 minus U. These have pieces that look like a combination of F plus and F minus times log 1 minus U. Okay? So it's just a few equations and few unknowns to totally determine the coefficients. All right, so let me summarize. So we have solved the problem. Okay, so now we know what the answer looks like, and we see that first of all there's this beautiful boundary differential equation that keeps track of time evolution. Okay, the analog of time evolution purely from the boundary point of view of what happens if you make one side longer and longer. Quite non-trivial that it's possible to find a solution for which the histories in U and V are compatible with each other, but it is. However, we also find that it's completely forced on us simply by the requirement of only having singularities in the obviously correct places, symmetry between U and V, and no spurious singularities. It's forced on us that the answer has these oscillatory pieces in the squeeze limits. Okay, so everything that we associate with the time evolution picture that would normally come from a time bulk integral, we have derived that, and we've derived without ever making any reference to time, just starting from this differential equation. Okay? Now, the last thing I should tell you, let me just say a few words. The only thing that you could complain about is you say, well, you got this differential equation by starting from the time representation to begin with. So how could we get this without doing that? And here, since I don't have any time to discuss it, I want to discuss something else in the next lecture, and it's a slightly technical anyway. What you can do is just begin. You see, what we did with amplitudes is we began to say, what should the amplitudes be? They're Lorentz invariant functions, so you first say that. If you just say Lorentz invariant functions, there isn't much you can say, right? It's too general. But then you say, since singularities matter, let's kind of filter what the answer looks like and how complicated the analytic structure is. So we began with contact interactions that were just polynomials. Then we had the next complicated thing that could have poles. Then at loop level, you can have branch cuts and so on. Now the analog of that exercise here is that we have functions that should be conformally invariant. Now these are conformally invariant, and we're thinking about the conformal symmetry in momentum space. And anyone who's familiar with these cosmological calculations, of course, there's huge similarity between everything we do in de Sitter and ADS and so on and so forth, and we're using conformal symmetry. The main sociological difference is that the cosmologists work in momentum space all the time, whereas most CFD people hate momentum space. Okay? They would prefer to work in position space or melon space, anything but momentum space. If you have an exact conformal theory, then it makes sense to diagonalize the dilations. For any realistic application in cosmology, inflation is breaking the conformal symmetry anyway. It's breaking it a little bit, but it's certainly breaking the scale invariance. The obvious symmetry that we have is the translations, and so these cosmologists are practical people. They talk to experimentalists, so you work with the symmetries you have, not the symmetries you don't. Okay, so that's why you have to go to momentum space, whether you like it or not. For cosmological applications, for example, you can't go to melon space in cosmology because going to melon space involves some analytic continuation of these formal functions. Our experimental friends aren't going to analytically continue anything for you, okay? So you work in momentum space. Momentum space is very practical, okay? Now, you might say, but there's actually, I think, a real opportunity here also for people who care about CFTs to invest some time thinking about CFTs in momentum space. The usual complaint is that even the three-point function is horribly complicated in momentum space for totally general operators because it involves integrals like that with 3 Hankel functions, right? So a big, horrible mess. It's true the 3-point function is a little complicated, but there's no free lunch. In position space for CTs, the 3-point functions are easy, but when you glue 3-point functions together, as Fernando was describing yesterday, you get complicated things in the conformal blocks. Whereas in momentum space, the 3-point functions are complicated, but gluing is simple multiplication, right? So you're really sort of shoving things around, but there's just vastly less that's been done with thinking about the structure of these things in momentum space. So while we know what 4-point functions look like in position space and in Mellon space, they're just poles and simple things, here we're starting to learn what 4-point functions look like in momentum space in conformal theories. And now you have to ask the analogous question. What's the analog of contact interactions? What's the analog of tree exchange? And so on. Okay? And everything becomes singularity. So the analog of contact interactions are things whose only singularities involve sums of all the energies. Okay, so that's the thing that, but then you can do that. Then you take a conformal invariance equation, you write it in momentum space, you apply it on functions that have that as the only possible singularity, the only poles they have is sum of the k's, and then you totally determine what the numerators can look like. Okay, so that's the first exercise. That's what contact interactions look like. I never mentioned a bulk. I never mentioned doing any integrals. I can just purely, by putting in a little bit of frisson of that by making an assumption about the simplest possible analytic structure. I can't not have any singularities at all just by dimensional analysis. So if I say the only singularities I have are the sum of the energies, then that tells me what contact interactions are. Great. I then move on from there and I say, what's the next simplest possible kind of singularity structure that I can have? Well, you notice that if you take the product of two 3-point functions, that's something that's conformally invariant as a 4-point function. And checking that that's true, the conformal invariance equation exactly turns into an equation of the form delta u minus delta v acting on the function is equal to 0, where we exactly discover the deltas that we're talking about. So they come straight out of the conformal invariance. And again, if you ask that you want the sort of simplest possible analytic structure, then you say that delta u on f should give you one of the contact things that you had before. And that's what we get. So the right-hand side, that's how you get these homogeneous equations. Okay, so that's the analog of filtering or understanding of scattering amplitudes, which again, that way of talking about this, the whole point was that we don't talk about the time evolution in the interior and so on. This is the way purely in the boundary data that you can put in information about causality. The analog, there are much fancier functions when it's conformal symmetry, but you can do exactly the analog of that game and discover these operators purely from a boundary perspective without ever talking about time evolution. Okay, so that's the perfect analog of what I was telling you. But I'll say one final thing before ending. And this is just a little amusement. I have no idea how general this is. But let's forget about all of that. Let's say that you just had this idea that somehow you're interested in 4-point functions like this, but there's this sort of somewhat magical thing. You want an equation that has a time in one channel, a U channel, a V channel, and they should be consistent with each other. So you're looking for some operator, LU, F equals U over U plus V, which needs to have the property, and let's say LU is some very general thing, just some polynomial in U, du squared, plus some polynomial du plus a constant. Okay? And we just want to demand that the same f that solves one solves the other. Okay? Well, that puts a constraint. It puts a constraint that LU minus LV on UV over U plus V is equal to 0. And that's just an algebraic equation on these guys. That's just the algebraic equation that U squared P of V minus V squared P of U plus U plus V U squared Q of V minus V squared Q of U is equal to 0. And that almost totally fixes the form of P of U. AU to the 4th plus BU squared QU is 2 AU cubed plus CU squared. And so our case before is just the special case where A equals -1 and B equals 1 and C equals 0. Okay, but in fact, they're all equivalent to each other with some simple changes of variable and shift eta. In other words, this differential operator comes from a bulk. It comes from a bulk with a Green's function of exactly the sort that we were talking about before, with more general eta, dd eta, and linear terms in eta. Okay, so that's what the bulk picture was buying us. If you ask what it's buying us that this consistency of the histories is totally manifest. But from every other point of view, we can sort of discover, we can even discover the form of the operator once we have this idea that we're interested in functions where time is encoded, several different times in histories are encoded in what happens as you make various side lengths long compared to the others by themselves. Okay? Now, I think it would be interesting to sort of explore this a little more generally. It should certainly be true for any point functions. And I think it's kind of a cool picture. This is again, us as cosmologists being paleontologists. This is how we see, this is how we have to disentangle. Someone hands us a whole big multi-point function. We could disentangle all the histories that contributed to it by taking some sides, making those sides longer than the other, and seeing do they satisfy a differential equation all by themselves. Okay? And by taking these various squeezed limits, we can find oscillatory pieces at the ends. Those would be various particle productions corresponding to more and more complicated processes where things go on shell. But even apart from that, we can see whether there are these ordinary differential equations that are satisfied as we take the various sides. And now, this was a very baby small example. By the way, that expression, as I told you, is also practically useful. If you just keep the terms up to k equals k and n from 0 to 2, and you compare this to the numerical solution of these equations, you can't tell the difference is already in a part in 100. So it's also practically useful, but I think it's also conceptually interesting, and it would be interesting to try to develop this time without time point of view a little bit more. All right, that's it. Thanks.
Some real quick questions.
Yes, no, I mean, so exactly. We could talk about all of these things in ADS as well. Okay, but as I said, but what we don't get in ADS is this is the magic of the two oscillatory solutions and all the rest of it. Okay, so.
Okay, so let's thank Nima again.